Good. Okay. So let's talk quickly about assignment 5. Oh, and you know what? Forgot to bring in those examples. Oh, no, man. Assignment 5 looks hefty. I guess it is, sort of. You could do all those problems, but for marks, there's really only the first 2 that you have to do. Okay. And then the rest of them, you just have to tell me what type of question it is. Right, so is it a 1 sample mean with sigma unknown, or is it a matched pairs, or is it a 2 sample means question, right? And tell me why, right? And that can be as simple as, well, we only have 1 sample, so it has to be a 1 sample means problem, right? Or matched pairs because we've made 2 observations on the same subject, right? So just justify which type it is, right? And the reason that I like to do this is not to torture you, but to have you read lots and lots of questions, right? Because once you decide what type it is, that's almost the hardest part, right? Figuring out, reading a question and figuring out what type of question is this, that's really hard, right? And so I like to give you tons and tons of them for you to read through. And if you want to work through them, you can, right? I've included the parts and kind of the questions that I would ask, right? So you could work through them. I don't have solutions for them, I don't think. Maybe I do. I don't think so, though. You could work through them as practice if you want to, right? But all I'm looking for on the assignment is what type of question is this, right? And why. Okay. So there's a little space after each one, right? Question 3 onwards, type and why, right? So you just tell me which type it is and why that is. Hold on. Uh-oh. There. Any questions about assignment 5? So these long answer questions that you're doing, it's going to be a matched pairs and a 2 sample means problem, right, for practice. Ooh. Oh, before I forget to hand them out, does anyone need to borrow a table? Yeah, but for those types, it could also be 1 sample mean sigma unknown. 5.1, yeah. So it's either 5.1, 5.2, or 5.3 for the types. But the questions that you're doing are only 5.2 and 5.3. Ooh. Anyone else need tables, formula sheets, fun stuff? Okay. Cool. Like I said, lots of papers. So what I did, because I wanted to try to speed things up a little bit, I printed out the examples that we'll go through. So today we're going to go through this 2 sample mean situation. We already talked about it last day, right? But we'll go through an example together, right? See how we kind of deal with all those values, right? We have sample means from both groups. We have sample standard deviations, sample sizes from both groups. So we need to be able to deal with that. But first, whoops, just do a quick review. I guess I should make a note about, so assignment 5 is due next Wednesday. November 28th. In class, of course. Do questions 1 and 2. Tell me the type and why for questions number 3 to, I don't know how many questions. 13. Giving you a run for your monies. Okay. So as a quick review, right, we talked about 2 samples, right? How we can collect 2 samples is, well, we could either collect 2 observations on the same subject, right, making matched pairs where we have 2 observations on the same subject. There's one kind of curveball for the types that you're going to look at, where it's not necessarily the same subject, right? But you will analyze the difference just because, I'll just tell you, it's the question 9, where you're comparing, I don't know, I can't remember what it's, the wind something, the wind speeds. So you want to try to figure out the difference on each day, right? So you're measuring on the same day, right? So even though you're looking at 2 sites, you're looking at the same day. What's the wind on this day? What's the wind on this next day, right? So that's a bit of a curveball, but that's still going to be matched pairs. Okay. So we just analyze the differences, analyze the mean of the differences. And that's what we went through last day, right? Section 5.2. Your null hypothesis is about mu diff equals 0. And what's nice, once you've identified, okay, I have matched pairs, you know your null hypothesis is mu diff equals 0. And mu diff, and your alternative is that mu diff does not equal 0. Right? So that's nice. And then you can calculate your t. Once you have your t, you know what to do. You go to your t table, find your degrees of freedom, right? And then you're back to familiar, more familiar territory. Right? So now, or we can have just 2 samples, 2 sample means, right? Where we have just 2 independent samples. And want to compare the means. And we talked about it last day, right? But we didn't get to an example, so we'll start with an example. So 5.3 example, 2 sample means. So now there's no way to say that, okay, this observation clearly matches up with this one and we find the difference, right? So think males and females, right? You take a group of a random sample here at the college, males and females. You could even have different sample sizes, it doesn't matter, right? And then you just want to compare the means of those 2 groups, right? Here, let's just talk about our example. I was going to make another one up, but it's early still. So we're talking about diamonds. So the weights of diamonds are measured in carats, right? So a 1 carat diamond is a certain weight. And then, so a 0.99 carat diamond is you can't tell the difference. Just looking at a 1 carat and a 0.99 carat diamond, you can't tell the difference. Okay. Thing is that a 1 carat diamond typically costs a little bit more than a 0.99 carat diamond. Okay. So what we've done here is we've converted the prices of each diamond to a point price, right? So how much does it cost per point if a 1 carat diamond is worth 100 points and a 99 carat diamond is worth 99 points, right? And so we've measured the mean point price for each of these diamonds, the standard deviation point of the point prices, right? And we collected 31 carat diamonds and 23.99 carat diamonds. So let's see if I can steal this. I forgot to bring it in. To print. Easy as that. Okay. So I'll just steal all this, but you have it, so. Got a little small. Okay, there. Right, so we have each of these groups and we have means and standard deviations and sample sizes for each of them, right? Because in our spreadsheet, right, we would have a column of the 1 carat weights or the 1 carat prices, sorry, and the 0.99 carat prices. Okay. So the question that we have to answer, is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds, right? What we would do with that information, we can kind of suss out later, right? If there's no difference in the point prices, then I don't know, why not go for the 1 carat diamond? Or why not go for the 0.99 carat diamond, depending on how you feel about it, right? Our job is just to be able to say, there is a difference between the point prices or there isn't, right? And then you can do with that what you will, right? There's lots of different spins that you could take. Okay? So use a formal hypothesis test with an alpha level of 0.05. Right? And so we're going to start by laying out our null and alternative hypothesis. Right? So part A. And this is kind of typical layout for all the information that you need for 2 sample means, right? Just kind of organized this way. You'll see in some of the types that you have to identify, it's in the blurb. It gets really wordy, but I like it in a table like that. Okay. So here we go. Step 1. We have to state our hypothesis. What's nice is that for 2 sample means, we know we're just going to compare the mean of one group to the mean of the other group. Right? And so on your formula sheet, H0 is mu1 equal to mu2, right? That's what you're going to have. Unless you prefer to do mu1 minus mu2 equals 0, that's fine too. Right? But I'm going to just use mu1 equals mu2. The important part is that we have question-specific subscripts on these, right? So we don't just use 1 and 2 because it doesn't matter which one is group 1 and which one is group 2. So we need to keep track of which one we're treating as group 1 and which one we're treating as group 2. Okay? So it's going to look like this. So mu of 1 carat I'll keep that as 1, equals mu of 0.99. Right, so instead of 2, I'm just denoting these kind of shorthand by the groups. Okay. Just make little notes here. Need to use question-specific subscripts. That's important. Later on in my formula, I'll probably just stick to 1 and 2, but for my hypothesis, I have to identify which one is which, right? Because saying mu1 is less than mu2, if you haven't identified which one is group 1 and which one is group 2, that doesn't mean anything, right? We want to know if the 1 carat prices are higher than the 0.99 carat prices. So how do we reflect that in our alternative hypothesis? Now that we have these question-specific subscripts, it's a lot easier, right? We want to know if mu1 is greater than mu of 0.99. I'll just make a little note here, right, that I'm going to use this as group 1 and this is group 2. Once I've decided which one is group 1 and which one's group 2, you have to stick with it, right? You can't jump around. But I don't think you would, but you can't. Do we have a one-sided or a two-sided test? We have a one-sided test because we only care about the one extreme, right? We have a greater than. If we had a less than in there, it'd be one-sided still, right? It's when we have a not equal to in the alternative that we have a two-sided test. We need to know if we have a one or two-sided test later for our p-value, right? And that's a really common question that I get. How do I know if it's a one or a two-sided test? So you have to go and look back at your alternative hypothesis. Usually, with a little bit of practice, people don't have a hard time figuring out what the alternative hypothesis is going to be, right? If you read enough questions and kind of set up enough hypotheses, it kind of starts jumping out at you, right? So setting up the alternative, people don't have a hard time with. It's the link between this sign here and whether it's one or two-sided that people have a problem with. Okay. So just make a little mental note. Okay, hypothesis. Great, done. How about step 2? Do the test. Do the test means calculate the value that follows the null and alternative hypothesis on your formula sheet, right? We're still calculating a t. It's just a little bit bigger than we're used to, right? But at the end, we're still going to have a t, and it behaves the same as all the other t's that we've had, right? So once we have that t, then we can forget about how we got there. So t is x1 bar minus x2 bar. Technically minus mu1 minus mu2. Okay. So technically it looks like this. Minus mu1 minus mu2, right? But this is equal to 0 since h naught is that mu1 equals mu2. And we always do our testing assuming that the null hypothesis is true. So if mu1 is equal to mu2, then that's always going to be 0. So that's why it's not even on your formula sheet. I tried to make it the least crowded it had to be. All over the square root of S1 squared over N1 plus S2 squared over N2. So we can calculate this. I was going to make a note about, because here I'm being sloppy, right? I'm not using 0.99. The only important spot is in your null and alternative hypothesis, right? So what I'm going to add here is need to use question-specific subscripts in our hypotheses. Okay. In our hypotheses. Because even I get sloppy with my t's, x1 bar, x2 bar. Okay. All right, so now we can plug these in. Hey, nice. So I'm saying the 1 caret group is my group 1. So my x bar for that group is 53.43 minus my x bar for my second group is 44.50 over the square root of S1, which is 12.22 squared, over N1, which is 30, plus S2, 13.32 squared over 23. So you want to make sure that you don't forget to square these values under there, but also don't forget the square root in the end. So if you don't know how to store values on your calculator, right, come see me after class and we can figure it out. I guarantee you your calculator can do it. Okay. It's just a matter of figuring it out. Okay, because you'll want to be able to store stuff. So 12.22 squared divided by 30. I'll store that in 1. (53.43 minus 4). So I get 8.93 up top. And then in the square root, I've got 4.9776, 13 repeating, plus 13.32 squared divided by 23, 7.71401731. You want to keep all your decimal places. Often what's happened in the solutions, if you're looking at those practice problems, because I program those solutions in R, it knows all the decimal places, even if it's only showing a couple. So sometimes if you're getting close to the same answer, but not quite, and you've rounded, then that's probably why. Okay. So plus recall 1. And then square root that. So I have 8.93 divided by 3.562531,505. .93 divided by that. What? 0.703613. 286. See if it's not right. Yeah. Don't know what happened. This one's been sticking. plus 3.1 square root yeah, sorry, not sure what happened. Kind of figured it out for a second there. 2.506644499. And that's what I have in my notes too, so. Phew. So our t then, right, we have to have at least 3 decimal places. So t, I'm going to use 2.507. Need 3 decimal places, at least 3 decimal places. Cool. So we've got our t. Step 3, find the p-value. Takes the same form every time, right? We have to, now that we have a t, we have to find our degrees of freedom, right? So let's make a note here. So using table C, with degrees of freedom equal to, we talked about this last day, right? We've got this kind of fun notation, the minimum of n1 minus 1 or n2 minus 1. Basically, you're taking the smallest sample size minus 1. Right? And that's just a really conservative estimate, but that's fine for working it by hand. Right? So degrees of freedom is the minimum of n1 minus 1 or n2 minus 1, which is the minimum of 30 minus 1 or 23 minus 1, which is the minimum of 29 or 22. The minimum of these two is 22. I'd be okay if you cut out 1 or, yeah, probably one of those middlemen. A little excessive. But I do want to see that you know that it has to be the minimum of n1 minus 1 and 2 minus 1. But then if you go straight to here, equals 22, that's fine by me. Pardon? Yeah. Cool. Yeah, so the minimum notation is probably not familiar, right? But just once you have these 2 values, you just pick the minimum, and that's the answer. Cool. We have our degrees of freedom, so using our table C with 22 degrees of freedom, we go in here, and we find and I'll just put the absolute value of t in the center here, t equal to 2.507 is between 2 values. Let's see here, 22. 22 is on the table, so we don't have to round down, right? We can just use 22. And 2.507 is between, just squeezing in, 2.183 and 2.508. This illustrates why it's important that we have at least 3 decimal places as well, right? Because if we had rounded this our t to 2 decimal places, we'd have 2.51, which would bump you over 1, right? And that's no good. So we have to have at least as many decimal places as we have in the table. So we have a one-sided test, right? We decided in our alternative hypothesis, so we need a one-sided p So our one-sided P is going to be between two values. Let's see here, find my spot again. My one-sided P is between 0.01 and 0.02. Nice. So now we know our one-sided P is somewhere in that range. Good enough for us. Step 4 is our conclusion. Remember, there's 3 parts to our conclusion. So first we have to say what our p-value is. How does it compare to the alpha level? Right. Second part is, what does that mean in terms of the null hypothesis, right? If it's less than the alpha level, then we have enough evidence to reject the null hypothesis. If it's not less than the alpha level, then we don't have enough evidence to reject the null hypothesis, right? And then does rejecting or not rejecting the null hypothesis, what does that mean in terms of the question, right? That's your third thing you have to touch on. So we use the same blurb that we have been using. So since our one-sided P is between 0.01 and 0.02, it is less than, I said, use a formal hypothesis test with an alpha level of 0.05, right? So it's less than 0.05, so it's less than our alpha level of 0.05. So that's the first part of our conclusion done. Which means, right, if the P is less than our alpha level, we have enough evidence to reject H naught. Right, we always have to state our conclusion in terms of H naught. Why? Because we've done all our testing assuming H naught is true, right? So it has nothing to do with HA until the very end. So which means we have enough evidence to reject H naught. If we're rejecting it, then we can say, well, in favor of what? In favor of HA. What does this mean in terms of the diamonds? The question was, this is where we answer the question, is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? Here you just reword the question as an answer. Yes, there is evidence. Blah, 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 blah. Therefore, there is evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. What would I do with this information? Well, if they look the same and the 0.99 are, we've just determined they're significantly cheaper, right? Then, I don't know, I'd probably just go for a 0.99 carat diamond. Valuable information, guys. Okay, cool. Any questions about that one? Nice. So what I wanted to show you just quickly was, we didn't have a chance to talk about it last day. Little quiz. I posted the test 1 and 2 stats. So we saw test 1, my quick analyses of test 1, your test 1 scores. And then I did the same thing for test 2. Okay. And so there's the distribution of the test 2 scores. Okay. Here's the summary. Okay. Then we said, okay, well, what if we look at your test 1 versus your test 2 scores, right? For each of you, right? Was there any improvement is kind of what I'm curious to know, right? And so because I'm looking at 2 measurements on the same subject, so you're the subject, you've got a test 1, test 2, right? That's 2 samples, right? But they're matched pairs. Okay? So what I did is I just pulled out the pairs, and what we'll see in the lab is just how to run this t-test, right? Where we just look at, okay, well, here's group 1, here's group 2. Are they paired? Yes. And I want a 2-sided test, right? And then, so a quick t-test like this gives us all this information. Okay, we're up to here. So it tells us, okay, we're doing a paired t-test. Here's the t that I calculated. Here's the degrees of freedom that I'm using, and here's your p-value, your one-sided p-value. Oh, sorry, 2-sided. I told it to be 2-sided. Also, just spits out a confidence interval as well, right, for your the mean of the differences, because it's matched pairs. Okay. So just, you can have a look at that. I did the calculations, right? So I'm giving you the X bar of the differences, the standard deviation of the differences, and the n of the differences. And then we could generate the same t calculation by hand. Right? I did it in R, obviously, but and then we said, okay, well, so test 2 had 2 versions, right? So is there a difference? Oh, well, what should we say about test 1 to test 2? There was no significant change. People kind of individually, yeah, you probably went up or down, yeah, right? But overall, as a group, you didn't improve significantly. Reason for that is maybe sample sizes, right? Small sample sizes. Okay. If we split you up by version, right? So if you were in version 1, there's the mean and the standard deviation and the sample size of group 1. Version 2, same thing, has a mean and a standard deviation and a sample size. Right? And so now we're doing a t-test of version, or of test 2 by version. Okay, we'll talk about that. We've seen that in the lab, but we'll leave that for the lab, but just so you've seen it. And then here, if you calculate your t, it's itty bitty. So there's virtually no difference in the means for version 1 and version 2, which makes me go, phew. What would I have to do if there's an actual difference in the mean scores? It's likely that one test was harder than the other. Right. And I would have to fix it. So I'm looking for no differences. Right. So it depends on the scenario if you're looking for a difference or no difference. So, cool. And then, of course, I gave you all the calculations in case you wanted to find t by hand, right? You need the X bars, 2 of them, the S's, the sample standard deviation for both groups, and you need the sample sizes for both groups. Right? Cool. Any questions about chapter 5? That's it for chapter 5. We're going to head into chapter 6. So, end of chapter 5. Chapter 5 is a big deal, right? It's where we start to see hypothesis testing and confidence intervals. Oh, I haven't finished the question. I need to do a confidence interval. Yeah, why not? That was just a teaser. End of chapter 5. It's on the horizon, though. Just one confidence interval away. Construct a 95% confidence interval. So a 95% confidence interval. That's what we want to do. Part B. Oh. Yeah, it's on that printout that I gave you. Maybe I'll just cut it. Copy. Okay, so part B. Now we're going to answer it using a confidence interval, right? So we can either do a formal hypothesis test with the p-values, right? Or we can do a confidence interval and then interpret the interval. And if our hypothesized values are inside that interval, then you don't have enough evidence to reject H0, right? So let's see here. Let's write out the formula for the confidence interval. Usually I would just go straight to finding T star, but this is our first time, so we have our formula that we're going to use, right, is x1 bar minus x2 bar plus minus T star times the square root of S1 squared over N1 plus S2 squared over N2. That huge square root looks familiar, right? What we can do, if you've already calculated it once, you can just say that I know that this is equal to, what did we say it was? Only if you've shown your work, though. It's 3.562531.505. 3.56, I'll forget. 3.5621, I've got it here. Uh, 2531505. I should have kept that. You can recalculate it, right? But hopefully it'll end up being the same. Right? So I'll just make a note here that this is 3.56 from part A. And you can do that on the final too, right? If you're finding that you have to recalculate something big like that, then just say, oh, I've actually already shown you what this equals. So I'm not gonna show all my work again, right? Here's what it is from part A, fine. Good. And this, we already found as well, right? That's the 8.93.
8.93 from part A. So that's allowed. So the only thing that we need to make this confidence interval is our T star. So we find our T star using table C. So using table C with degrees of freedom equal to, and again, I'm just going to say the minimum of N1 minus 1 and N2 minus 1 equal to 22 because I've already shown my work once. So if you've already done it once, then you can be more slack about showing your work a second time around. And a confidence level, and a confidence level of 95%, we find that T star equals, so we're going to go until we hit 22 degrees of freedom. 95%, 2.074. Great. So now we can piece together this confidence interval. So we have, yeah, I'll just write it again. You don't have to. X2 bar plus minus T star S1 squared over N1 plus S2 squared over N2. That's a square. This we said was 8.93 plus minus 2.074 times 3.562531,505. Clean this up a bit. So I have 2.074 times 3.562531,505. I should have stored it, but I forgot. So I had to type it. No biggie. So plus minus 7.388690341. This I will store in one. Because I have to do 8.93 minus this and 8.93 plus this. Oops. So 8.93 minus, recall 1.541309,659 up to 8.93 plus, recall 16.31869034. If you remember that these are dollar amounts, that's great. If not, you probably would have gone to 2 decimal places anyways, right? So now that we have this interval, we have to interpret it and then talk about what does it mean in terms of our null hypothesis, right? So first we'll do our interpretation blurb, which is always the same, right? So we are 95% confident the interval from $1.54 to 1632 captures what? Captures whatever I told you to make an interval of. the difference in mean point prices of 1 carat diamond and 1 carat and 0.99 carat diamonds. So captures the difference, oops, in mean point prices of 1 carat and 0.99 carat diamonds. Nice. So what does this mean in terms of the hypothesis, right? Are they the same? No, because the difference in mean point prices, we're 95% confident that both of these values are above 0, right? So because our interval is consistently above 0, right? The 1 carat diamonds, just looking at how we found our differences, are consistently higher priced per point than the 0.99 carat diamonds, right? So if 0 was in this interval, then we would say, oh, well, then, yeah, no, there's no difference between these two groups, right? Because this interval is consistently above 0, right? Then we say that, no, there is a difference. In fact, the 1 carat diamonds are higher than the 0.99 carat diamonds. Okay. So since this interval is consistently above 0, we have enough evidence to reject H naught right? H naught was that mu1 equals mu2, right? Or if you want to think about it as mu1 minus mu2 equals 0, might be helpful in this case, right? Because that's why we're concerned about it being above 0. And since the difference in means is above 0, we can say the mean point prices of 1 carat diamonds is higher than 0.99 carat diamonds. 0.99 carat diamonds. You're going to arrive at the same conclusion, right? It's just a matter of how you get there. Right? So if you're contradicting yourself, then, well, one option is that your confidence interval doesn't match your alpha level that you used in your hypothesis test. But for the test, right, or I think maybe not on the assignment. I might have forgotten to change it to make them matching. Anyways, keep an eye out for that. Right. But a two-sided alpha level of 0.05, right, means you have 0.05 split up between the two tails. And so 95% in the center, right? So they're equivalent. Cool. Now we're done, chapter 5. Any questions now? Cool. Now I'll put in my little, oop, Eon. Not sure what happened there. end of, oh, I know what happened. Squish them together. End of chapter 5. So one little twist, and I'll have to give you guys a revamped formula sheet, is that we're actually going to do 6.1 and 6.2. I know. It's because we cut the binomial. We are going to do chapter 7. But probably just 7.1, 2, and 3. Yeah. But they're funner. No more hypothesis testing in chapter 7. Yes. Yeah, I can't remember how many, but there are.
Like in subject, you know how many marks the file have? Like 100?
Oh, I don't know. It should be, often it's around 90 marks, but depends. So, getting into chapter 6. So chapter 6 is dealing with proportions. Okay. And proportions are fun because it's a lot of kind of accessible data, right? So who would you vote for, right? Categories. And so, or 4 out of 5 dentists recommend whatever, right? So these are all proportions, right? So where we're talking about some number is in some category, right? Out of a total sample size. Right? So you go out and, well, right now, are you going to vote proportional representation? Yes or no? Right? And so now we've got 2 categories, and we can analyze those proportions, right? We could analyze just the proportion of people who vote for proportional representation, right? And then, or we could, doesn't really make sense to compare the 2 groups, right? There's a 50-50 split. If there was a third option, then we could compare them. Right? But what if we did, I don't know, what are 2 proportions we could deal with? Proportion of blonde hair to brown hair. That's kind of boring. Anyways, so we're just going to deal with 1 proportion or comparing 2 proportions. So chapter 6 is on proportions. 6.1 being 1 sample proportion. Proportion. So proportions come from categorical data, right? Whereas we've only been dealing with means questions, right? What's the average of this? What's the average of that? Right? And those all come from numerical data, right? And so proportions come from categorical data. Right, the proportion in each category. And I'll just say, whereas we have been dealing with means, which come from numerical data. So just like before, where we had population information and sample information, right? We need notation to keep those 2 separate, right? So we have a population proportion is going to be denoted by a lowercase p, which is confusing, or if you want to use pi, you can. I use just the lowercase p. Right? So the reason I'm throwing pi out there is because we have been using Greek letters for population stuff, right? And so it makes sense to just use pi, right? Greek letter for p. But for some reason or another, as proportion analyses kind of evolved, started using p instead. Not sure why. But if you want to use pi, that's fine. But as you'll see on your formula sheet, your null hypothesis is about p and not pi. So I use p. And then we have a sample proportion. Which is going to be a p hat. We can't use p bar anymore, right? Because p bar would mean the average of p, which doesn't really make sense, right? So we have to use a hat instead. So p hat is your sample proportion. Your sample proportion, so your p hat, oops, is the number of successes in the sample over the sample size. The successes being whatever you're interested in, right? So are you interested in the proportion of males being born, right? Then the success would be how many males are being born, right? The opposite of that would be how many females are being born, right? So if you're talking about, okay, well, how many females are being born, then the success would be the number of females, right? So the successes is just whatever you want to talk about as your proportion. Okay? So success will be whatever we want to talk about as our proportion. So just to reiterate, right? If you're talking about, okay, I want to know the proportion of males being born, right? So you go down to the hospital and a male born, that's a success. A female born, that's a failure, right? It's not meaning what you set out to look for, right? So anything that's not a success is a failure. Right? Let's say, I don't know, you want to look at the proportion of blue eyes, right? Someone has blue eyes, that's a success. Anything else would be a failure, right? In this situation. So what's nice is that it boils it down to success failure, right? There's no other options, right? So you have some number of successes and your total sample size that you looked at. So a pretty cool thing is that proportions will follow a normal distribution. What? That makes no sense. It's true. Proportions will follow a normal distribution, but there are some assumptions that we have to check. So I haven't made you check any assumptions. I find that that's kind of, I don't know, bogs you down a little bit, right? But for proportions, we will have to check assumptions just because it is important. Okay? So proportions will follow a normal distribution if assumptions are met, or if the following assumptions, I'll just list them here. If the following assumptions are met. First one is we have to have a random sample. Fair enough. That's kind of been an underlying understanding that we developed in the very beginning of the course, right? We have to have random samples so that our samples represent our population, right? So that's fine. So we have to have a random sample. Great. Second one is that, and this one's kind of counterintuitive, is that your sample size has to be less than 10% of the population. Meaning we can't have too big of a sample. And that's kind of counterintuitive, but you'll never have a sample size that's larger than 10% of the population, right? Especially if you're talking about Canadians or Americans or whatever, right? To have even 10% of the population would be a huge sample size, right? And so we'll never get there, right? So usually these assumptions, we just talk about them. Yeah, the sample is randomly collected, done. And sample size of 570 Americans, I think is the example we've got coming up, or 670 maybe, is less than 10% of the population of Americans. So we just have to check those. And here's where it kind of deviates whether we have a confidence interval that we're about to do or a hypothesis test that we're about to do. Okay. So, and then for confidence intervals, the third thing we're going to check is that n times p hat has to be greater than 10. Which just means that we have to have more than 10 successes because if you go back to your formula for p hat, right, p hat is the number of successes over the sample size n. So if you multiply that by n, those n's will cancel, and then you're just left with a number of successes, right? So what we're saying is that, okay, well, if we're going to use this data to talk about the proportion of successes, we have to have at least 10 successes in our sample, right? And same idea, NQ hat, we haven't talked about Q yet, has to be greater than 10, but more than 10 failures. Yeah, it's a Q hat. So where Q hat is 1 minus P hat, right? Or it's the proportion of failures. So on your formula sheet, right, I have the general where Q is 1 minus P. So Q in any scenario, right, Q hat is 1 minus P hat, Q is 1 minus P, Q naught is 1 minus P naught, right? It's always just going to be the opposite. So if I told you that there were 48, or the proportion of males was 0.48, the proportion of females, you know, or you would just think, intuitively, you just know it's 0.52, right? The opposite of that. So that's all the Q is saying. It's the proportion of failures. Okay. So that's for confidence intervals. For hypothesis testing, to check our assumptions, our third assumption, so 1 and 2 are the same for both scenarios, right? And then for confidence intervals, we've got step 3 and 4 that we need to check. Is NP hat is greater than 10 and NQ hat is greater than 10. And if we're doing hypothesis testing, the assumptions we have to check are going to be that NP naught is greater than 10. And the fourth one, NQ naught is greater than 10. So what does this mean? It means that the expected, or more than 10 expected successes and more than 10 expected failures where P naught comes from the null hypothesis H naught that P equals P naught. So it's going to be the proportion that we want to compare our sample proportion to. To be completely honest, if you just wrote these out exactly like you see them here, I don't know. I'd say that's 1.5 marks out of 2. I don't know. I can't really. You did it. Ideally, what we'll do in the examples, right, is we'll calculate the number of successes and the number of failures, the number of expected and the number of expected successes and failures. But in the final exam, I'll mark nicely. So just having these kind of locked and loaded, I will ask you to check the assumptions on the final, right? And so just have these ready to go. Write them down. See what happens. Once you have them down, though, you'll probably just have the values and you can fill them in, and voila, you've done it. Okay. All right. Anything else before I? That's probably good. We'll keep going, probably with the example next day. Any questions before?
Next Wednesday, right?
Yeah. With 6.2, I'll bring that on Monday. I guess I'll see you guys in the lab.